Good morning, everyone. I'm thrilled to be here today to present the first solution for the 7th LSVOS Challenge RVOS track, SA2VA. This work is the result of a great collaboration between our team at Wuhan University, the University of California, Merced, and Nanyang Technological University. The topic we are tackling is referring video object segmentation, or RVOS, which is a critical task demanding fine-grained understanding of both visual content and natural language instructions. Today, I'll walk you through how our proposed method, SA2VA, which stands for Segmentation Augmented and Selective Averaged SA2VA, successfully addressed key limitations in existing multimodal large language models and led us to the top position in this challenging competition. Let's start with the incredible results we achieved. Let's get straight to the achievement. We are immensely proud to announce that our proposed method, SA2VA, secured the first place in the demanding 7th LSVOS Challenge RVOS track. As you can see on the official leaderboard, our model achieved a leading JNF score of 67.45. The JNF score is the primary metric, combining region similarity, JACAD, J, and boundary accuracy, F-score, F, and this result is a strong indicator of our model's robust performance. Crucially, this score significantly surpasses the runner-up's performance by a margin of 2.80 points. This demonstrates the effectiveness of our approach in handling the diverse and complex scenarios present in the challenge dataset. To understand how we achieved this significant breakthrough, we must first look at our foundation, the SA2VA baseline model, and its inherent limitations. Our winning solution is built upon a strong foundation, SA2VA framework. This model is a prime example of a modern architecture that leverages the power of foundation models for complex tasks like RVOS. SA2VA essentially couples an MLLM with a powerful segmentation model, SAM2. Here's the workflow. The MLLM takes the language query and a set of sampled video frames as input. Its job is to perform the high-level reasoning, understanding the text and locating the target object in the video. The MLLM then outputs a special single, SEG, token. This token is not the final mask, but rather a compressed, high-level representation of the target object's location and properties across the entire video. This single segmentation prompt is then passed to the SAM2 decoder, which handles the precise, pixel-level segmentation on all the frames. In essence, the MLLM determines what to segment, and SAM2 executes how to segment it accurately. While this architecture is innovative and effective, it harbors two critical limitations, particularly when dealing with long, complex videos, which we will discuss on the next slide. As powerful as SA2VA is, it faces two significant challenges when dealing with the kind of long, dynamic videos typical in the LSVOS competition. The first limitation is input inefficiency. The SA2VA framework was originally designed to sample only 5 frames per video to be fed into the MLLM. For short clips, this is fine, but for videos that can be hundreds of frames long, sampling so sparsely severely limits the MLLM's ability to capture the global context and the entire object trajectory. It loses crucial information about motion, appearance changes, and interactions. The second, and perhaps more critical, limitation lies in the output mechanism. Relying on one single, SEG, token to represent the segmentation information for the entire video is a massive bottleneck. This single token struggles to encode the necessary changes when the object changes position dramatically, changes shape or scale, even disappears and reappears, a common occurrence in real-world videos. To break these two bottlenecks, we developed the Segmentation Augmented and Selective Averaged SA2VA, or SA2VA. Our solution fundamentally re-architects the way the MLLM processes video and generates segmentation cues, which we will now explore in detail. Our segmentation augmentation strategy consists of keyframe compression and scaling, SEG, tokens. Next, I will elaborate in detail. First, we introduce keyframe compression, or KFC. This mechanism allows us to dramatically increase the amount of temporal information the MLLM sees, while respecting its limited input context window. We first partition the entire video of T frames into n equal length clips. Each clip has C frames, so T equals n times C. Instead of feeding all C frames individually, for each clip, we compress the frame set into one composite image. As you can see on the slide, we concatenate G times G frames within the clip, into a single, large image, ICAT. Then resize this concatenated image down to the original size that fits a single image slot in the MLLM's input, ICOM. We specifically designed the C frames per clip using the formula C equals G square plus 1, where G is the compression grid size. This effectively boosts MLLM's temporal receptive field from 5 to 2n frames. As shown on the slide, the MLLM's visual input is no longer the sparse 5-frame sample. Instead, it is the highly informative 2n KFC frames. Specifically, for each of the n temporal clips, we feed in one keyframe and one compressed frame. This gives the MLLM a rich, compact view of the entire video's temporal dynamics. With this comprehensive input, the MLLM generates the set of n segmentation prompts. The final step is decoding the masks. Since we divided the T original frames into n clips, we now use the corresponding SAM2 decoder for every frame ij belonging to clip I. We use the SEG hidden states S I to decode the mask, resulting in M J I. We set the total number of frames sampled, T, to 100. We used a number of temporal clips, n, equal to 10. This means our MLLM generates 10 specialized, SEG, tokens for each video. Finally, we set the number of frames per clip, C, to 10, and the compression grid size, G, to 3. Our segmentation augmentation module drastically improves the model's ability to generate better segmentation prompts. However, the final crucial step is robustly applying these prompts at test time, especially across videos of varying lengths and complexities. So we introduce or inference sampling strategies. We explored 5 distinct strategies, each designed to optimize the selection of frames T for the MLLM input. Uniform is the standard approach. It evenly divides the original video and uniformly samples frames within each clip. Uniform Plus is an enhanced version of Uniform. For shorter videos, frames near clip boundaries might be sampled twice. We average the resulting masks from those two, SEG, tokens, a simple yet effective way to fuse boundary information. QFrame, we first use an external module QFrame to select the T frames most relevant to the text query, and then process them using the Uniform Plus strategy. Wraparound, this strategy is designed for long videos. If the video is longer than T frames, we sample cyclically. Wraparound Plus is the mixture of wraparound and uniform. This slide shows the critical ablation study comparing our approach against the baseline on the ME-VIS valid U and valid splits. The first row is the original SAW2VA baseline without our segmentation augmentation. We also see that the inference sampling strategies we introduced further refine this performance, consistently pushing the score slightly higher, with Wraparound Plus achieving the peak validation score of 71.37 on valid U split. It surpasses the baseline over 10 points. This confirms that segmentation augmentation is our main engine of improvement, providing the majority of the performance boost. While segmentation augmentation provides the primary boost, we noticed that different models and sampling strategies have different strengths, particularly when facing the diverse, challenging videos of the LSVOS challenge set. To capture these complementary strengths, we utilize selective averaging. For every pixel in the output mask, we aggregate the results from various sources, multiple models and multiple sampling strategies. Crucially, this is a weighted average. The results from different models and strategies are assigned specific weights. Finally, we apply a threshold. If the weighted average value of a pixel exceeds 0.5, its final mask value is set to 1, otherwise, it is set to 0. This ensures the final prediction is robust and synthesizes the best information from all our optimized components. Selective averaging is the ultimate refinement, leveraging the diversity of our outputs to squeeze out every last bit of performance on the demanding challenge leaderboard. This slide presents the final results of our selective averaging strategies on the challenge set. First, let's look at the best performing single configuration before any averaging. This model, already benefiting from segmentation augmentation and optimized sampling strategies, achieves a competitive 65.66 JNF score. This is where most single model solutions typically cap out. Now, observe the impact of selective averaging. By intelligently weighting and combining the outputs of multiple models and various sampling strategies, we see a crucial performance jump. The JNF score rises from 65.66 to our winning score of 67.45. Our analysis shows that selective averaging provided a substantial secondary improvement of about 2 JNF over the best single model result on the overall challenge set. To conclude, let's quickly recap how SAW2VA addressed the core limitations of the baseline SAW2VA. The initial challenges were twofold: sparse frame sampling, which limited the MLLM's access to the global video context. Relying on one single, SEG, token for the entire video, which struggled with temporal object changes. We addressed these directly through two major modules. First, segmentation augmentation, our main engine of improvement. This innovation, powered by keyframe compression, KFC, and scaling, SEG, tokens, achieved a massive over 10 JNF improvement on valid set. Second, selective averaging, which used 5 inference sampling strategies and a weighted ensemble approach to provide the final refinement, resulting in an additional 2 JNF improvement on the demanding challenge set. By strategically integrating MLLMs with segmentation models and introducing these temporal augmentation and ensemble strategies, we successfully developed SaSaSa2VA, the first-place solution for the 7th LSVO's RVOS track. Thank you all for your attention. We believe SaSaSa2VA offers a robust and effective framework for advancing grounded MLLMs in video segmentation tasks. The report and code are publicly available, and we encourage you to check them out.